The best way to model heat transfer through an egg would be to consider it in spherical coordinates and with steady state heat transfer, as that would allow us to look at it as a one-dimensional problem with the variables only varying with the radius. For this problem, we are to derive the steady state one-dimensional heat conduction equation from an energy balance. And here I started with the general balance and then moved towards an energy balance, substituting in some thermodynamic information with the heat transfer, which then allowed some further substitutions given known equations for heat transfer here. We can also substitute in geometric equations for the area normal to the heat transfer over this this boundary core here for both the volume and the area. And then making the substitutions and simplifications, I got to a point where there was a step on the solutions I did not understand, so I didn't want to go further and I didn't have time to consult for help. This problem involves a solar heating system with water tubes, an absorber plate, and some insulation, and we are tasked with finding proving that the temperature profile matches this given statement, and also finding the value of heat flux Q dot naught. Starting with the second derivative temperature, we have that it is 0, and then we take the integral twice effectively, and then we can apply our boundary conditions, specified temperature and specified heat flux, in order to find those constants. From there, we can prove that we have a formula for the temperature profile that matches what is given. And then, in order to find Q naught, we can sum up all the different Q dots that we have from solar absorption, radiation, and convection with our given information and formulas we know, including Newton's law of cooling, and that for heat flux radiation, and then solve for that Q dot naught. Here we find the differential for heat conduction and the boundary conditions for a resistance wire in water that is resulting in heating. And we have our conditions in the one-dimensional steady-state equation for heat conduction in this cylinder, and then we can make substitutions given our knowledge of heat transfer here. And then following simplifications and integrating twice, we find a relationship for the temperature profile, and from there we can evaluate using our boundary conditions of thermal symmetry and the fact that we know that at the R naught, the outer surface, we have cooling that conforms with Newton's law of cooling in order to find our constants. And then we have our differential here, our boundary conditions of thermal symmetry and convection, and the equation for the temperature profile and the temperature at the center line. Air in contact with water that is saturated is not going to have a mole fraction of merely 1, as saturation does not imply predominance of that species. We can do VLE calculations in order to find the fraction of water in the air, and then we can actually apply those for a physical scenario here and come with actual numbers. Places I had difficulties were in the first problem, as I could not figure it out, and then I couldn't interpret the solution here with the limit as delta R approaches 0, and also with being able to explain these all within 4 minutes.